All right, so welcome back to the final lecture, Lecture 30 of Physics 325. Today we're just going to talk about the last subject, which is aberration theory. So, kind of throughout the course, we've been throwing around the small angle approximation like it was nobody's business. I mean, we've worked in the so-called paraxial approximation, where sine theta is approximately equal to theta, for the majority of the course. And it's typically worked really well, and it's produced an accurate description of all the optical phenomena that we've studied. But in this final lecture, we're going to kind of pay our dues and go beyond the paraxial approximation and find out what some of the consequences were of making that approximation. And in short, we're going to find that points are no longer mapped directly to points, like in a perfect imaging system, but they're mapped to regions which are systematically biased in one direction or another, and we will no longer have perfect images. The imperfections are known as aberration, and this study of how they affect the images is called aberration theory. There's also going to be aberrations due to wavelength dependence of the index of refraction. Remember, a lens works by being a particular index of refraction with a particular shape, such that points are mapped to points. And if our index of refraction depends on wavelength, as we found when we studied dispersion, well then our lens is going to look different for different colors. But that's what we're going to talk about at the end. It's called chromatic aberration. So let's start with monochromatic aberration. I mean, we're going to plug in n and we're just going to assume that it's constant. So let's go back a few lectures to lecture 27, I believe it was, and look at our derivation of what a lens actually does when we derived our matrix optics formalism by looking at a refracting surface. Here's our refracting surface that we derived, and we applied an ultimately lazy version of Snell's Law, where we said Snell's Law was n1 theta is equal to n2 theta. And that worked out well to derive these system matrices. But today, we're going to start with our monochromatic aberrations and go beyond that so-called paraxial approximation. So before, where we had the embarrassingly lazy version of Snell's Law, we know that it's really sines, and that's what we want to plug in when we do this refracting surface here, this one here. Now, numerically this is no problem, and this is how ray tracing programs work. But if we want to get an analytic expression, it turns out that it's difficult or impossible even to derive analytic closed form expressions of what exactly happens to arbitrary rays going at an arbitrary angle in the system when you use sines. There's just arc sines and arc tangents and arc coses everywhere. It's a total disaster. So we're going to do the next best thing. We're just going to use a higher order Taylor approximation. So our new version of Snell's Law will look something like this. Or equivalently, so we have this extra deviation. And when we derive the analytic expression for what happens at a refracting surface, we get a slightly more complex polynomial term. We get a polynomial which tells us where images are mapped. So just to show you what it typically looks like when you do this analysis, it looks something like this. Okay, so we have a beam coming in at an arbitrary offset from the axis, and it's going to hit this optical system at some point, and then go to some height y prime and some deviation x prime. Those are the different planes we're going to look at. And when we do the analysis, of this system, we get a complicated polynomial expression. This is what the actual analysis looks like. See, we've created all kinds of high orders. And what we're going to do is we're just going to keep every term up to third order. And these are going to lead to the so-called third order aberrations. We're going to collect all the terms. And when we do that, we get the first order term as we expected. Plus we get a polynomial term up to third order, which has 5 different coefficients in front of it. And those 5 different coefficients are 5 optical aberrations. And those are what are known as the 5 third order or Seidel aberrations. Now I went back and forth a bunch on how much math we should do here. It turns out that it would be a lecture and a half probably to derive this, and it would really just be collecting terms and doing algebra and banging our heads. So we're just going to look at these more operationally and see what understand what these aberrations actually do. So there's 5 of them, and this is described in some of the supplementary texts, namely Pedrati cubed, and this one that I just showed you is due to Smith's book. I'll include a link in Core Spaces if you want to have a look through this. Oh, excellent. Bad image. Okay. Teaches me to upgrade Windows before doing the lecture. So let's get back to it. There's these 5 monochromatic aberrations, and we're just going to enumerate them and see what they actually do. So the first one is known as spherical aberration. And what we're going to do is we're going to consider a point that's right on the optical axis, and look what happens when we focus, bring it to a focus with a lens. So there's my point, and we're going to bring it to a focus. So for very, very small angles, sine theta is approximately equal to theta is a very good approximation. And we essentially get no deviation from our paraxial theory. But as we get further and further up this lens, the curvature becomes more and more. The angle, theta, is going to increase, and this sine theta equals theta becomes a progressively worse approximation. So we get something that looks like this. So the further away we are, the more sine theta is not equal to theta, the more deviation we get. We're going to get a different focus than we would have otherwise. And this just gets worse and worse, so we get further off axis, and our theta increases. So our beam, as we have it here, is going to focus at different points based on where that ray, or rather a ray, will focus at different points based on how high up the lens it hits. So the result of this is that our focus is not infinitesimally small, but is spread out. So I wrote a little Python script which should illustrate this. Let's have a look. So what this does is it just takes a lens which is plano-concave, to make it very simple. I should draw what I'm actually plotting here. What the script does is it takes a lens which is shaped like this. First side is flat. As flat as I can draw it. And the rays are going to come through and they're going to strike at an angle. I did it plano-convex so that I could calculate the physical angle with respect to the normal and directly do Snell's Law. So this is what we get when we run that. And next to it, we're comparing the paraxial approximation. We get just directly doing Snell's Law, which is a good approximation, which is better approximated by the theta cubed term at the interface here. Remember before, this is saying that theta 1 is equal to theta, or n1 theta 1 is equal to n2 theta 2. Well, this is just physically doing the refraction at that spherical surface. And we see indeed that the further off axis we get a different focus. And we do not get a perfect focus there. So let's get that over to our notebook here. Getting back to it, we have the Snell's Law version of optics, in which case we have, let's see if we can draw the image as we see it. Out here, we'd have some sphere coming in, some disk of light coming in hitting the lens. Here, we'd also have a disk. So a beam would be confined to this region here. And then we would not get all the way to 0, we'd get to some circle. So it would be a certain size there, smaller size there, and here it would be a very, very small but non-zero point, and then it would increase. This point, this minimum image size here, has the nice name circle of least confusion. Whereas for our paraxial approximation, it goes to a infinitesimally small point. So there are special lenses that we can use that are shaped to avoid this spherical aberration. They just have to adjust the curvature at these higher up points up here. If we can adjust this region such that it is corrected for, we can get rid of spherical aberration. And these are called A-sphere lenses. Here's an example. So this is a company that sells these things, Edmund Optics. And they basically just have a differently shaped region which maps all those points, all those rays coming in to a given point, and those are called A-spheres. Here's one that we use in our laser here. We develop our own lasers in our lab, and it's very important that we don't have things like spherical aberration, which would deform the optical beam. So we use A-spheres from a company called Thor Labs, and I believe it is one of these models here that we use. Yeah, so they're not astronomically expensive, about $80, and they come in a mount that you can just screw in to find the exact right location to focus it. So that's how we can get around spherical aberration. Even if we do use a lens without spherical aberration, an A-sphere, we will still not get an infinitesimally small point. Why? Because diffraction. Diffraction will lead to an airy disk, because that is the image of our aperture, right? The Fourier transform of our aperture is what we see at focus, and that is going to be an airy disk. So if we do have a optical system which is not limited by its optics but limited only by diffraction, we very cleverly call this diffraction limited. And diffraction limited optical systems are kind of the gold standards. If you want to buy a really expensive optical system, you better check that it's diffraction limited. And that term gets thrown all around a lot. Oh, we use a diffraction limited lens here, or we have a diffraction limited imaging system. Okay, so we're going to move to the next aberration. Consider a point like we did before, but now let's consider it to be off axis. A point which is off axis will get a different sort of aberration, and it's known as coma. Coma can be seen as a magnification, or transverse magnification, that is dependent on how far up the lens your rays are when they refract. So let's think about that. Here's what an image does. So let's think about that. Here's what a lens does. It's going to form an image at some point. And for nearby rays, i.e. for paraxial rays, we're going to focus to that same point. This is just our standard picture of when we're imaging something, right? Here's something we're actually imaging. So if we look at face on, this whole central region of the lens is going to focus directly to a point. Okay? But now let's look at points which are now at larger angles with respect to the optical axis. For example, this point here. This is a region here at a given radius of curvature away, and it's going to have a different magnification. That's what this coma is describing. So it's going to focus up here. So we're actually going to image that. That disk, rather, is going to get imaged right here. Now, further, it gets worse the further we get. So let's look at even further along rays, or rather rays that are even higher up. That's going to have even more of a deviation of its magnification. So these rays in this disk here, they're going to get magnified even further up. So the image plane, here looks something like this. So what we're going to get in general is an image, a point, which is going to get mapped to a funny shape like this. So I'll have a very sharp point in this tail. And that, well, I guess it looks somewhat like a comet, and that's where the term coma comes from. You'll get these rings which have a higher transverse magnification, so that means they're higher up on the axis, and we're imaging the lens, or that portion of the lens, as it gets higher and higher up. And that's known as coma. You can also get special lenses which minimize this effect. Usually you have to use multi-lens systems so that you're not going too far up in the lens. And I got to think, when I hear the term comet, this must have been a real pain for the initial astronomers that were just understanding their optical systems, and they were looking for comets. And they were like, oh, I found one. And they point their telescope directly at it, and the comet disappears. But then there's another one to the left or to the right of it because those images will be off axis. So tough times being an early astronomer. Okay, so a similar effect happens when you're looking, when you've tilted your lens. Maybe you're on axis, but you're looking at a tilted lens. You get a different sort of effect, which is also due to this off-kilterness of our optical system. You get an effect known as astigmatism, which is the third Seidel aberration. And the whole idea with astigmatism is, through hook or crook, for some reason, you have that the focus along one axis, say the x-axis, is not equal to the focus along the orthogonal axis. And this can be due to tilt, or it can be due to a fundamental asymmetry in your lens. Maybe instead of a soccer ball shaped section of a lens, a spheroid, you have a rugby shaped section of a lens. That will lead to different radii of curvature in different directions, and therefore astigmatism. And this is actually a very common occurrence in eyesight. So in your prescription, remember we talked about prescription a few lectures back, 2 lectures back, where we looked at the dioptric strengths of the lens needed to correct for hyperopia or myopia. Well, a similar things. Let's load up that picture. Let's see if we can find it. I think I just had it as a link. Well, we'll just do a Google image search for prescriptions. Eyeglass prescription. There's one. Good. Okay. So, is this the same? John Smith. That's a better pun this time. Okay, so here we have our dioptric strengths of 2 diopters and 2.75 diopters, and I do not want 10% off my next order. Sorry about that. So, and then we have these these next 2 numbers, which is the cylindrical lens, and it has an axis. So this is the axis that you're going to put a cylindrical lens to, and this is the focal strength of the cylinder. So a cylindrical lens is going to be like a lens, but only in one dimension, and it tells you which axis that should be applied to correct for the astigmatism of your vision. I am one of those people that has an astigmatism. So I can actually fix my eyesight, which I don't know how I discovered this, but by pushing on my eyeball in one direction. I'm not wearing glasses, I can see perfectly well. It just looks kind of awkward walking around life through there. But that's how to fix it, is you fix the fundamental asymmetry in the imaging system. So let's look at what that would actually look like if we had a beam that was going through an astigmatic. If we're going through an astigmatic imaging system. So we'd have a lens here. So our beam would be perfectly symmetric. It would go through and let's say it focuses more tightly along X. So it would come to that focus along X here, and it would still not be focused along Y. It would start to come out, and then it would look focused along it would hit the focal point along the Y direction before coming back out. So we'd see a funny type of focusing as we went through the lens if we're looking head on the beam. So this is kind of confusing the way I've written it, but this is the cross section, or the face on view of the beam. If you can picture that, it would be a sphere. Initially, it would be perfectly symmetric initially. It would focus along X first and become very tight along the X direction, and then it would gradually unfocus, and it would focus along Y. So if we looked along X, the focus would look like this, and similarly for the y direction. So the next aberration, the fourth Seidel aberration, is called field curvature. And field curvature occurs because the focal plane that we've been using in our geometric optics is not actually a plane, but rather a curved surface. So the point which all rays focus to is actually a curved surface called a Petzval surface. Or Petzval surface, I don't know how to pronounce that properly. It's one of those words you've only read, you haven't heard anybody say. Anyway, and therefore it will lead to images which are more or less focused depending on where we put our surface. So typically in a camera, we have a CCD or film which is in a plane, and if we move the camera so that the center is in focus, we'll have this picture here, but the periphery will be out of focus. We can zoom our CCD closer, or a lens closer to a CCD, and then the periphery will be in focus, but the center will be out of focus. And that's known as field curvature. A nice solution to this is to have a curved surface, and our eyes, in fact, accomplish just this. You can also have more complicated imaging systems, multi-lens imaging systems, which minimize this effect. Okay, so finally, the fifth aberration is known as distortion. So distortion is due to an increasing or decreasing magnification with distance from the axis in the image plane. Very similar to coma, except now we're looking at different different magnification in the image plane. So take for example imaging a square grid, such as this. If we have an increasing magnification with radial distance away from the center, as we get further and further away, we have a distortion which looks like this, which is called Pincushion distortion. And if we have a decreasing magnification, we get what's known as a barrel distortion. And this is a common flaw in optical systems when you use just one giant lens to do all the work. Typically, the way to get around this is to use smaller focal length lenses of specific shapes, or even if you're just using normal lenses, which are not A-spheres, you can have weaker lenses and a bunch of them so that you share the refraction amongst many surfaces, and you're never too far away from that central point. So given these 5 aberrations, what do we have? We had spherical aberration, coma, astigmatism, field curvature, and distortion. That covers all the third-order corrections to our Snells Law when we're looking at an image formed by a refractive surface. You can kind of get around that by using a smaller central region of your lens, but then you have less light collecting power, which is an issue. More commonly, you use multi-lens systems, and let's see if we can find that a few lectures back. Here it is again. That's precisely what something like this beast does here. We use a ton of different lenses, and you can numerically optimize the system so that it minimizes these 5 aberrations. And that's why you pay the big bucks for the big optical systems, but you get a nice image out of it. You also might want a given field of view and a given amount of light collecting power. But optical systems can be quite complicated, mainly to get a more and more increasingly small spot size, i.e. the mapping of a point to a very small region. Okay, so suppose we use this lens system, this complicated beast here, and we take an image. We use it, we form a camera, we take a picture, and we test it with a laser, this very fancy laser, and it all works. And then we put it in our camera and take a picture, and this is what we see. We take a picture of this dude, and this is what we see. That is not a perfect image. So what went wrong here? Well, there's another aberration which we didn't talk about, which is called a chromatic aberration. So we can understand chromatic aberration by looking at what we had for our focal length of a refracting surface. So if we remember that, we had f was equal to the radius of curvature divided by n minus 1. We'll be back in the paraxial approximation now. Don't worry about aberrations, monochromatic aberrations. But what do we use for n here? If we recall from our from the section where we studied dispersion, remember we had electrons that were basically on springs, and that led to a finite response time of an atom to an electromagnetic field, which led to a frequency-dependent and therefore a wavelength-dependent index of refraction. Well, if we just plug that in, we now have r of n of lambda. N is no longer a constant. It's going to be a different n for red than it is for green, than it is for blue, and therefore we'll have a wavelength-dependent focal length. So we'll have something that looks like this. We'll have a red light coming in. It'll refract. And then it'll refract again. Similarly for the other side. And then we're going to have a similar picture for blue, but it's going to be a different focal length. So I've kind of greatly exaggerated this, but this tells us that we'd have a different focal length for red than we did for blue. And that is called chromatic aberration. And that leads to this effect here, where we have the image which falls on different points. This is kind of a contrived picture. It's a very bad chromatic aberration. It's normally more subtle than that, but it's there. And that's what it is. How do we fix it? Well, there exists a type of lens called an achromat, which is formed by wedging two lenses together in order to cancel out the effect of chromatic aberration. And that is the fix. So the fix is what we call something called an achromat, or an achromatic lens. This, when you have two lenses together, is called a doublet. So the general way to do it is you have something with low dispersion. And we have a low dispersion positive lens, meaning it's converging. The focal length is greater than 0. And that might be made of just silicon dioxide or something. And then following that, we have a high dispersion negative lens, or a diverging lens. Typically it'll be flint glass or something like that. It's very dispersive, so that our red beam goes along its merry way, and it refracts more weakly, as we showed above. But that goes both ways, so it also bends back more weakly for this negative lens, and it's going to focus to a given point. We have our blue beam here, and it's refracted much more strongly. But now we get the blue and the red focusing at the same point because of this doublet which corrects for it. And you can have triplets as well, and air-gapped doublets that do a better job. For this particular lens, we see yellow is somewhere in the middle, but we can use a more fancy, sophisticated achromat to correct for that as well. So the achromat is a special lens you can use to negate the effects of chromatic aberration. And most eyepieces are achromatic doublets. We talked about this last class. Instead of using a single lens as an eyepiece, often you use at least a doublet eyepiece that can get rid of some of the chromatic aberrations as well as the monochromatic aberrations. This goes for the objectives in a microscope too. If you have a highly dispersive objective, you get really bad chromatic aberrations in your image. And you can buy these off the shelf. They're typically two lenses that are cemented together. So if we go back to our site that we were showing before, where I tend to buy my optics for my lab, we have these cemented achromatic doublets. And you can buy them off the shelf. You can even have these triplets, which do the same thing, doublet pairs, and you can make fancy eyepieces and more sophisticated beams by combining more lenses this way. Here you can see there's really just two lenses which are wedged together. Okay, and that's it for aberrations. That's all we're going to talk about, and that's it for the course as well. Now, as you know, the course came to a slightly abrupt end. We would have talked about things like fiber optics and more advanced subjects, but I feel like with the material you've covered, you have a very solid understanding of third-year optics.